I'm Martin, Solutions Engineer at SurrealDB. I'll be talking today about knowledge graphs for AI agents. Keep an eye on the chat on the right. Make sure you add any questions you have. We'll be responding them in the chat. And yeah, also I see familiar faces there in the chat already. Hi, Santi. And yeah, let us know where you're connecting from. And yeah, if you have any questions, feel free to ask. Cool. And yeah, while more people connect, let's get started. So first, a quick introduction about SurrealDB. SurrealDB was became open source in GitHub maybe around 3 years already. It became very popular on the Rust community. It was featured in a couple of YouTube videos back then, and yeah, it got a lot of traction. And I started using it actually like 3 years ago already, and yeah, never stopped since. We are almost reaching 31 stars in GitHub. I think we're already there. We've had some traction in enterprise customers. We've been deployed in embedded systems, on the edge, highly distributed architectures. It's yeah, a very like flexible database to deploy. It was built on Rust, so it can be compiled to different architectures, which allows it to run embedded even in the browser or in highly distributed environments. It's multi-model, which means in the same engine, you have all the modalities you can think of, like relational tables, also document tables, like any JSON blob you want to store. You also have time series, geospatial, so you can query coordinates, for example. You have vector search, which is very common now in AI use cases, full text search that enables you hybrid search together with full text search, and key value, of course, and then graph is one of the most common ones now for AI use cases as well. So it's very common to mix graph, full text search, and vector search when you are doing RAG systems, for example. And so it's very convenient to use SurrealDB because you only have one database to hold all those three modalities. While relational and document are also very popular, also within RAG use cases. We have also some AI here and machine learning here, because you can actually, if you go down the path, you can actually import ML models into SurrealDB and have some inference functions running while you, for example, insert a new record. You can do like sentiment analysis and things like that with your custom ML models. And yeah, so that's SurrealDB at a glance. So let's get into the topic of knowledge graphs. So what is a knowledge graph? Let's start with the formal definition taken from Wikipedia. Also to demonstrate that knowledge graphs is actually not a new thing now in the AI use cases. This became very popular a couple of decades ago already, and was very popular in the Google search engine, for example, so that it keeps like concepts related, so that your results are more valuable in that sense. It represents and operates on data, right? So basically the graph is a representation of your knowledge, where you have concepts related to other concepts or entities related to entities using different types of relationships. But of course, it not only stores data, but it also is used to navigate your knowledge graph, right? So when we talk about doing multi-hop graphs, it's basically you're navigating the graph hopping from one entity to another through a specific relationship, and you can do many hops as you like, depending again on your use case. It also allows you to keep it updated very easily, which is one of the nice things of using a knowledge graph together with a vector store, because a knowledge graph is very easy to update, especially if you, for example, take decisions based on some knowledge you may have in your graph. Then you can actually reflect that back. And in the future, you can have also like a bit of traceability. In general, I think knowledge graph, it's a tool that allows you to be very creative to solve your RAG issues, and also to can kind of represent different information that is sometimes not as easy to represent when you only have vector stores, for example. So let's start first by knowledge graphs, and I want to show two different specimens to contrast one with each with the other, because in this area, in this topic about how to build a knowledge graph, it actually depends a lot on two things. First, your data set. Yeah, there's a lot of different types of data sets, and on the other hand, your use cases, right? So it depends on your data set, the nature of your data, and the nature of your use case, or let's think about the types of questions a user is going to ask your chatbot. Then depending on those two things, the way you build your knowledge graph, it can be very different. And also in some cases, maybe a knowledge graph is not the ideal solution. It's sometimes not enough, and sometimes just an overkill. So on one side, we have knowledge graph like this, which is generated from very explicit data in your database. So for example, assume you have an e-commerce database where you have tables, mostly relational data with transactional data as well, where you have products that are part of categories. Then a product may have reviews, and a product also may have an order, right? So every time a customer creates an order, then there's a relationship between that order and the product. And that also contains some metadata, like how many items were sold in that specific order. And then below orders, you may have like customers or any other types of relations. So here, for example, if you generate a graph like this from transactional data, it's very obvious what your entities and relationships are, right? It's mostly like a map from your relational data into your knowledge graph. On the other hand, you can have more graphs that are not as explicit in your original data set, and that you may need an LLM to infer some of the entities and some of the relationships as well. This one is a hybrid because you have things that are very explicit in your data, like, for example, the author of an article or a document, and the year may be also very explicit in the header of the document. But chunks, concepts, and probably companies are things that are going to be inferred by an LLM, like analyzing the document or just specific chunks. And then the relationships as well, like, for example, leader in, that relates company with concepts. Actually, this one may be different, like probably like a concept, maybe this is like a company is leader in a specific solution or a specific industry, right? So concepts will hold industries, for example, and then a company would be a leader of that industry, which is something that the LLM inferred from that company, coming from a specific like document chunk. So as you can see, some of these relationships and entities can be inferred, are not very explicit on the dataset. But then coming back to the other thing you need to have in mind is your use case, right? What's, for example, if you're building a chatbot to do RAG, what are the questions that your users are going to ask, right? So do you need to actually identify concepts, companies, chunks, years, right? So for example, if you are in building a chatbot for customer support and you are generating a graph from support troubleshooting emails or Slack messages or whatever, and you want to in the future respond to some of the same questions, then probably you would want to generate an inferred graph where you can hold like the product the question is about, probably even the version of the software the user is running, and then you also want to infer like if a step in the troubleshooting process was actually a solution or not, so that you can mark solutions in the knowledge graph as like good solutions or just bad troubleshooting steps and so on. So it really depends on your use case. So why do AI agents need knowledge graphs, right? Sometimes I get this question and people are argue that maybe a good vector store with very high dimensional vectors are good enough. And sometimes it's true, right? Sometimes a vector store is just enough to build the right context for your chatbot to be able to generate a good answer, right? But sometimes what I've seen is that at scale, vector stores get you probably a lot of chunks with a high accuracy, but they basically compete with each other. So sometimes you have context clash or even context confusion where the LLM just gets a lot of chunks to generate an answer, but maybe there are too many chunks. All can be correct, but there may be too many chunks. And sometimes LLMs don't like big contexts and things that look like can contradict themselves. So that's where knowledge graphs come into play, because they allow you to be more deterministic and also like to trim down like the vector space so that you can more accurately give the LLM just a very specific chunks of data that are required to generate an answer. In this case, this is a nice analogy. I think LLMs are very good storytellers. They're very good at generating an answer. But if they don't have any like factual data or context from your RAG system, right? If they don't have like facts or good context, they are just going to hallucinate an answer. So the idea is to put them together, right? So have a very good storyteller generating answers, but a very good knowledge graph that, as deterministic as possible, generates good contexts for the LLM to generate a nice story. In this case, yeah, for example, we have the previous knowledge graph as an example where you have reviews for products that are part of an order. So it's very easy and very deterministic to get the bestseller products from your knowledge graph, right? Because it's just relations and metadata give you the latest, the orders from this month, then the bestseller products. So if you run this query, you're going to build a very accurate deterministic context for your LLM to summarize all those reviews. And just to make it clearer, if you imagine this without a knowledge graph and only using vector stores, from the vector store you may get summaries that are semantically close to the question. So somehow it's going to give you an answer, but it's going to completely hallucinate what the most popular products in your store are, right? And if you have a very big vector store with a lot of information from your company, maybe it's already ingested like slides or presentations or even conversations from your internal Slack or internal Notion pages where there's some information about this month's bestseller products. So it's actually possible that using only vector store, it can actually find this information if the information is somewhere in that vector store. But it's not going to be very accurate and definitely not deterministic, right? And it also would require some human to actually have presented about the bestseller products of this month so that that information goes somewhere and gets ingested in your vector store. But if you have a knowledge graph like this, which is hopefully even the same database as your transactional data, it means that this will be just completely up to date, and it will be very deterministic way to get the bestseller products and then summarize the best reviews. So definitely no chance for hallucinations in that use case. And coming back to vector embeddings, as I said, if you have very big vector space, you may have very dense neighborhoods, like you can see in this diagram. Imagine you get a lot of documents or chunks inserted in the same very specific neighborhood in your vector store, probably because they're talking about the same topic, and you get more and more chunks very close by. It means that whenever there is a query that is also positioned in that specific point in the vector space, there's a high chance to get a lot of results from a vector query, right? So it's going to start having issues by picking which is the best chunk to use to generate an answer. So adding graph to that helps you trim down the results. So imagine you create relationships between some of those nodes. Again, I'm assuming we are in SurrealDB, so you have vectors and graphs in the same data, in the same records. So a single node can be vector embedded and will be connected to different nodes through different relationships. So it means that you can like do a vector search query, but use the graph relationships to trim it down, right? So for example, if you are in customer support or product support, right? Someone is asking about that my mouse is not working, right? How do I troubleshoot Bluetooth issues, for example? So from the prompt, you can infer the product and the issue, right? It's a mouse and it's related to Bluetooth. So you could have that represented in your knowledge graph. So for example, all the nodes with troubleshooting guides and resolutions to issues that are ingested in your store can be related to the specific domains and products. So basically, all those chunks that are related to Bluetooth issues for your mouse would be also connected to the graph node that is about that specific product, and also specific to troubleshooting guides. So you can do a query to the vector store, but trimming out or just including in only the nodes in the vector space that have a relationship to the mouse product and also to troubleshooting information, which will then reduce a lot the vector space. And then these high dense neighborhoods are going to be less dense, and then it will be easier to get a very accurate response. And also, you're only taking into consideration chunks that are related to a specific product and to the specific domain of troubleshooting articles. So it's not going to have a lot of context clash in that sense. Yep, this is basically a lot of what I was telling, there is no right or wrong way or easy way to say if you're good to go only with vector, only with graph, with both, or even add full text search to the mix. But as a rule of thumb, if your agent just needs to answer questions based on a manual like troubleshooting or customer support, vector store could be enough. Depends on the scale and depends on if you have a lot of products, a lot of domains, a lot of things in the same store. And that's typically what you would use only the vector stores for. But if your agent needs to make decisions, follow policies, or manage complex workflows, then definitely you would need a knowledge graph, especially if you need like explainability or traceability related to those decisions. And sometimes, or probably a lot of the times, actually, if you're in a use case where you're taking decisions, maybe you're also storing them back in the knowledge graph to inform future decisions as well. So in that case, if your knowledge is also very dynamic and you want future retrievals to be related to previous retrievals, then definitely you also need a knowledge graph. Cool. Let's see if there is any questions there. Yes, there is a question from Sebastian. Hello, wie geht's? I would like to know how GraphRAG works. Is it basically a nested SurrealQL query with, let's say, 3 hops, document, page, section, plus embedding? Yes, so I don't want to move my slides forward just in case of the spoilers, but with SurrealDB, you can do a single query that, for example, you can do a vector query to find the nearest node from your prompt. And from there, you can, in the same query, like get siblings, right? So for example, if you have a specific relationship coming out of that node that is embedded, then you can do that hop to the siblings in the graph. So for example, you can get to a chunk based on vector search. So you get the chunks that are similar to your original vector, the vector prompt. And then you can get very easily, for example, the related documents by doing a graph relation, by navigating through a graph relation. But of course, you can do multi-hops. So you can not only get the document that is connected to your chunk, but also like concepts that are connected to your chunk. And the relationships also will be very important, right? Because concept could be related by a relationship that explains the concept with the chunk, or a relationship that is not like an explain, like concept explains chunk, but maybe it's an author that wrote the article, or a possible reference to a product, right? So yeah, hopefully I answer the question, but if not, hopefully going to have time to show some example queries that are sometimes pretty long, but it's the beauty of having our own SQL-like query language is that we can have all those modalities in a single query, but also we have nice like array and object functions that allow you to even build a nice JSON format and give that as an output of the query. It can be as complex as you want, and trust me, I've seen queries that are very complex in a good way, because people get very creative. So it's usually the simplest form of hybrid queries have been when you combine full text search with vector. But I've seen like multi-hybrid queries where you can combine full text search with vector, with graph, and even relationships and everything in a single query, and do even the re-ranking and dedupling data in the same query. So yeah, let's get to that point and show some sample queries. Continuing with how to build a knowledge graph, it's basically an ETL process. E is for extraction, T for transform, and L for loading. So let's keep that popular acronym and let's dive into it. So extraction is about parsing, chunking, embedding, and entity and relationship extraction, right? So, and there's a lot of use cases. So some use cases don't need you to parse data, but imagine the worst case scenario where you have a PDF that has images, tables, text, figures, everything, right? So it's a multimodal PDF. So you definitely need to parse it to translate the PDF into readable text, like plain text, readable for an LLM. So the issue there is that if the PDF has images, you need to decide what you want to do with the images. So you can caption the images, and then in the plain text, you add the caption of the image so that the LLM, when it reads the text, knows that there was supposed to be an image, and then it will read what the image is about instead of actually reading the rasterized image, right? So you just translate the images into captions. That works in some cases. In some other cases, you want to actually have the real image and have an LLM be able to see the image, right? And in some other cases, the opposite. You can just remove the images and forget about them, right? In some cases, right? So that's, I think, the worst case scenario, where you have multimodal PDFs and tables. You can also have tables within PDFs, and tables are also very tricky. But again, depends on the use case. Then chunking is the process of making text just readable, like smaller, so that you can actually read it and within the context window. So LLMs you cannot pass a 100-page long PDF to an LLM and ask a question, right? You need to give it just a couple of paragraphs, probably. That depends on how big the LLM is and how capable it is. But also there are research papers that have demonstrated that the smaller the context you give to an LLM, the better the result. Of course, it has to be small, very accurate and precise, and contain all the information required to actually generate the answer. So the smaller the chunk or the context, the better. So you get smaller contexts by chunking PDFs, right? So instead of shoving the whole PDF, you just create a context based on those chunks. So the issue then is, how do you generate chunks that are actually meaningful, that are self-contained, that make sense, right? So again, there's a lot of strategies: recursive, structural, semantic, agentic, and so on. I think you can categorize them by accuracy and cost. Usually there are strategies that are very, very, very cost effective. So you can just think of the easiest one is just count 1,000 tokens and split the document there, and then you have one chunk, and then split again after 1,000 tokens more, and then you just continue chunking like that, right? So and you can see some issues with that, right? You may just chunk something just between the most important part, and then you get a very important thing just split into two different chunks, right? So that would be a shame. And so that's very cost effective, very quick, very, very cheap, but probably you're get some of those issues. Structural works it's also very, very cost effective and better than recursive, because basically it's going to just chunk whenever there is a paragraph change or a new headline or a page, right? So it's going to use the structure of the content to decide when to generate a chunk, and also based on token windows. Semantic is a better one, but then you start adding LLMs to the mix. So it means it's going to be a bit more expensive because you're using GPUs, you're using tokens, you're paying for the LLM, right? And it's not a big LLM, so it's a embedding LLM actually, so a very cheap one. And it's similar to how you generate vector embeddings for semantic search or vector stores. But basically, it calculates the embeddings of a chunk and compares, or a paragraph, and then it generates the vector embeddings for the next paragraph. And then based on the similarity, like the semantic similarity between both, it decides if like they're very similar, it keeps them both in the same chunk. But if they differ a lot, then it will decide to chunk them in between, right? So based on semantic similarity, it will just chunk your data, which is really, really cool. Very, very well balanced. Not very like brute force oriented, and also not very expensive to run because it's a very cheap LLM. On the other hand, you can go full agentic and let a very big and expensive LLM decide how to chunk your data, right? And probably in the future, with even bigger and better LLMs, agentic will be very good actually to do this. But it also depends on how much you are paying for that, right? There's also some papers already about not chunking at all and just relying on the LLM to read the whole document. But of course, there is a limit. But it will then, on the fly, decide what chunk to extract to use it for generating the answer. So basically, you do not chunk during extraction, but you chunk when you are doing the RAG. But again, this is very new, also probably very expensive. And usually, for now, I would suggest you just chunk your data in this extraction step. Then embedding is just generate the vector embeddings of each chunk, at least in this case. At the moment, we have only chunked. But then if you do entity and relationship extraction, which is generating the nodes and relationships for your knowledge graph, probably you also want to embed some of those entities, right? So now here you can embed chunks and you can embed entities. So moving back to one of the diagrams here, right? Actually, the blue nodes are the ones that are like part of the vector store. So in this case, I would embed the review. I would embed the product, probably based on the product description, and I would embed the category. This means that, and here as well, company, concept, and chunk. This means that you can access this graph by doing a vector search to reach one of the blue nodes, right? So here, for example, you can do a vector search to find a specific topic or concept that was mentioned in one of those reviews, and then you can do a graph query to get the products that are related to the reviews that mentioned that specific topic. So imagine someone is reviewing your products because they have a very specific issue. Like let's say it's not compatible with Mac OS or something. So you can use vector search to find all the reviews that are mentioning compatibility issues, and then you can do a graph query to get the products related to those reviews. Then since you can do multi-hop graph queries, then you can also go through the orders and then see if the order dates are on the same month, and then you can see, okay, yeah people are all those complaints about compatibility issues are actually from this month's orders because we shipped something wasn't fully tested yet, for example, right? So that shows you starting from vector search into multi-hop graph query in the single query. Okay, moving forward, we reach transformation. So now we finished extraction. We have entities, we have relationships, we have embeddings, chunks, we have everything in the database. But now, basically, we just take a step back, make a pause, and clean the data, basically. So here is where we have a chance to find duplicates, do ontology alignment, and inference and enrichment. So basically, deduplication and ontology alignment are very similar. Basically means that if first you want to find things that are duplicates, so Arnold and Schwarzenegger are the same person, but they are just stored as different entities in the graph. So you want to merge them so that the governor of California is also a star of Predator. And so if you ask this to your chatbot, it will agree. But if you don't merge Arnold and Schwarzenegger, it's going. If you ask your chatbot is going to say, no, there's different people. One is Arnold and the other one is Schwarzenegger. Probably the LLM with its parametric memory already knows that it's the same person. So that's not going to happen. But as an example, you get the point, right? And ontology alignment is basically making sure that the entities and relationships that were inferred and extracted from your documents make sense and are aligned to your schema, right? So that you have places, you have people, you have movies, you have companies, and everything fits into that ontology. And you don't have animals, for example, here. And if animals are not part of your ontology, then you have now chance to see what to do with that. Maybe you just want to ignore that or review why was an animal mentioned, right? Just as an example. And also the relationships, right? You may have like a preset, a predefined list of relationships you want to have, like capital of, governor of, star of. But sometimes the LLM will just infer a relationship that maybe you don't want to store or you don't care about, and then this is the point where you can like decide, like, should I include this, or is it an error, or should I just ignore that? Basically, the transformation step is a time during the process to make sure you clean everything up, and not only clean but also enrich, right? Sometimes you want to add more information to the nodes. Like in LightGraph, if somebody knows about LightGraph. I'm going to give a bad example first, right? So when you generate a knowledge graph like this, you get a chance now to infer things, right? So you could infer, for example, as a summary of the movie Predator. And when you insert this node in the graph, you can also insert a summary, which is generated by the LLM, right? So that may help you, right? And in the future, if you create a query, maybe the summary will be embedded, so you can use the embedded summary as a way to do vector search and then start your graph query from there, right? So that sounds pretty good, right? The issue is that sometimes if you are generating summaries, for example, those can include hallucinations, right? So you are storing in your knowledge graph things that may be hallucinated, and eventually your chatbot may get that hallucination and use that hallucination to answer a question, right? So you want to avoid that. I mentioned LightRAG. That's a paper that was pretty popular, I'm not sure, maybe a year ago. They do a little bit of enrichment and they generate summaries and keywords and concepts and build a graph around that. But basically what they do, instead of using those inferred attributes as part of the knowledge that is going to be sent to the LLM, they only use those inferred properties to navigate the graph. So for example, as I mentioned, if you infer a summary of the movie Predator and you use that as an entry point with vector search into your graph, and then you do graph queries, multi-hop queries from there, that's great, because you're going to find relationships and nodes and chunks probably that are going to generate the context for the LLM. But the summary is not actually going to be passed down to the LLM. So even if the summary had an hallucination, it may help you just reach the graph and do a hybrid search, but you're not giving the summary back to the LLM. So the hallucination will just die there and not be passed as a context. And then the last step is loading, which is the fun part because we get to insert data into the database. When you generate or when you insert knowledge graphs in general, usually the term is triplets. So you see that in this pseudocode. And basically a triplet is a list of three things, which is a node, a relationship, and another node, right? So here in SurrealDB, nodes have IDs like any other record. So we have a record ID for the first node, then the name of the relationship, and the second node. For example, this would be a review ID, reviews, product ID. And this is pseudocode, but I think it's almost production code anyway. And here you can see that you are storing nodes, and then you insert and embed those nodes, and then insert the relationship that ties both nodes together. Here you can see that I am using a function that takes the node and is going to generate the embeddings vector and then insert the node with the embeddings vector. So this is a nice utility function that does a lot by itself. And here you can see if I am inserting a node that is not meant to be vector embedded, it's just going to insert the node as it is. This is assuming that you have in your knowledge graph nodes that you want to embed, but not all of those nodes. For example, you may want to embed products using their product description, and they are related to an order, but you don't want to embed orders. They're just transactional data. Cool. So let's see if there's any other question. I think we're good. And yeah, let's continue. So now more in depth in practice. This is an example of how a knowledge graph, very simple knowledge graph, can look like in SurrealDB. This is a screenshot from our GUI, the Surrealist, GUI as in graphical user interface. So you can download Surrealist and use it to see your database schema, explore your records, run queries, create cloud instances, and so on. So here you can see some things. You have dashed borders. That means I am running in schema-less, which means that I can add any data to the table, like MongoDB, for example, and not only to the specific columns that I have predefined. And then you can see also dashed lines, which mean record references, record links. For example, here the queue has a reference to a document. So this is this dashed line, right? While the solid lines mean proper graph relationships, right? So here, for example, you see this chunk is connected to concept through the mentions concept relationship, right? So relationships are actually tables in the database with an in and an out. And you can actually also add more properties of metadata or to the relationships themselves. Let's go to the next. There you go. This is just a quick demo video, just to show you around Surrealist. It has this graph visualization page where you can toggle tables, you can zoom in, you can right-click, click on inspect. Here you can see that this specific node has the embeddings. So this is showing the multi-modal feature of SurrealDB. And that's one of the queries. These are some util queries I usually use. So basically they allow me to see what my process ETL, what my current ETL process looks like. So I can see how many pending chunks are there and the concepts that are being inferred and so on. This is another query that allows me to see, I think this one is to see, to find concepts that are linked to more than one chunk or one document, because during the process, I wanted to see if does it make sense to infer the concepts the way I'm inferring it. So I wanted to see if concepts are actually related to more than one chunk, right? Because if you only have concepts that are related to one chunk, then basically there's no benefit of inferring those concepts, right? But if you have concepts that are related to a lot of chunks, then it means that the concept is like a real concept that's part of your domain and will help the RAG work. So now navigating the graph. Navigating the graph, there are two ways. The traditional RAG way, which is where you have a user sending a prompt, let's say to a chatbot agent, and then it will retrieve data from the database. And then let's say you get 5 chunks with very high score, and then those 3 chunks are going to be passed to the LLM as context. And then the LLM will use your prompt, that context, to generate an answer. Let's say about a customer support question about troubleshooting or something. This is traditional RAG, right? Again, a little bit simplified. Now we have Agentic RAG that looks like this. If you are familiar with modern LLMs, you know that they can use tools, right? So Claude, OpenAI, most of the providers, you will see in their models that they are have this special feature of calling tools or calling functions. Basically, that allows an LLM to decide to use web search or to decide to use an MCP. And in this case, this is a multi-agent RAG system. So let's say the system is the whole chatbot application and it gets a prompt. So there will be a couple of agents doing different things. So let's assume you have an agent that works as a router. So it will get the prompt and the agent will figure out, like, is this a customer service request, or is this like should I route this to a different department, or is this about mouse and accessories, or is this about software, right? So you can have an agent that takes those decisions. You can have then other agents that now, based on your domain, they will basically query the knowledge graph to then generate the right context. So as you can see, web search is a very common built-in tool that LLMs have. Sometimes you don't have to provide the web search tool. That's just already embedded in the model. MCPs are very common, and those you need to connect to your agent in a way. depending on the framework you're using, if it's LangChain, Camel, Agno, Crew, or Pydantic. And another way is to create your very custom tools, or in this case, this would be like a tool set for SurrealDB knowledge graph. And within that tool set, you can have very specific tools, like a tool that it's like pre-created to do a hybrid search by topic, or do a monthly bestseller review, right? So depending on your use case, you may have very custom specific tools, but also you can have a very like open-ended tool and allow even the LLM agent to write the SurrealQL query that is going to be sent directly to the graph. And here it is. So this is the one example query where you can see both vector and graph happening, which is maybe looks scary, but it's not really that scary when you compare this with the alternative, which would be to have a vector query going to a vector store in one database and then get the results. So basically you have now a query language and your Python code, and then with the results, you again need to do something with that and do a graph query to another database. So there's a lot of glue code that you need to add in between, and then manage different database instances and so on. While with a single query, you get everything from one place. So here you can see that if you're familiar with SurrealDB, you will notice this line 84 is the vector search one. For those not familiar with SurrealDB, this is, you can see this is not SQL. This is similar to SQL. We call it SurrealQL. And this is the notation for vector search. So you're doing here basically, if you have an embedding vector coming as a parameter, as an argument to your query, this coming from the vector embeddings model, basically it's asking for the top 5. So here 5 is the K value, and with an effort of 40, right? So the higher the effort, the more accurate but slower it will be. 40 is a good balance. Sometimes if you don't need that much accuracy or a full list of all the neighbors, but you are optimizing for latency, you can set this up to 17, for example. That's super fast. And depending on your chunks, you may get already the ones you're expecting to get. So here, basically, this inside select is going to find the chunks that are similar to your prompt. And then that is used by the outer select, which is going to relate those chunks to their original documents, so that in the result of this select, you do similarity search against the chunks, but the result you actually get is the document. So you know which document is the reference. Then you can also limit by a threshold. So you don't want scores below 60%, for example. So you make sure that whatever you're generating and giving to the LLM as context have high scores. And then the outermost select here, you can see an array transpose, which is basically just rearranging the results I get from this select into a nicer form. So basically, I'm creating here a JSON object that contains contents, scores, chunks, and the chunk indices. So here you can see the result. It's basically a list of chunks where I have the highest score. And basically, this is representing a single document. So it should be below if I scroll down. And within, I get all the chunks grouped because I only care about the document because I want to use the document as a reference in the answer. But here you can see the chunk that was they had the highest scores maybe was this commencement information. So here you can see it's a good example of hybrid query vector search with a very simple graph query, but also you are like rearranging the results. And this is how you provide this as a tool. In this case, I am using Pydantic. So I created a retrieve tool, which is just going to take a search query and use that to run a query like this. So basically, by using this decorator, this retrieve tool is being registered as a tool to my original agent. And using the doc strings, the agent will know when to pick this tool. So whenever it wants to retrieve documents from the knowledge graph, it will know to call this tool. And it will know that the only argument is the search query, which is super straightforward. And yep, the code is very simple. Basically, just going to embed the query. And this embedding here, the result of the embedding model, is what gets passed in line 84. And then the results are just concatenated and sent to the LLM to generate the answer. So basically here, the LLM will have the name of the document. So it will use the contents of the chunks to generate the answer, but also it will be able to say to the user which document was the source for giving the answer. Okay, this is also a good example. This SurrealQL, this is a tool that has like hard-coded query, right? So the query is in the code. The only thing that's not hard-coded is the embedding and optionally a threshold. So it means that it will run this query every time whenever the retrieve call is called. But you can also have the LLM generate the SurrealQL, right? So this query doesn't have to be hard-coded. The LLM can just write its own query for very dynamic questions, for example. In that case, of course, the LLM may hallucinate a little bit and generate queries that don't work, but it's all about the system prompt and how you optimize the system prompts. If you're going that route, I suggest you create some few-shot examples. So give the LLM examples of queries similar to the ones you expect it to generate. And based on those examples you give, the LLM will more accurately generate queries. I think we're reaching the end of the time we have got today. So let's see, I think there's no more questions in the chat. This is last chance for you to ask anything else. Here you can see an example run. This is the agent that has already my tools registered. And here you see the system, not the system prompt, but the instructions. I am telling, use the knowledge base to generate your answers and mention the document in the answer, because I'm assuming the user wants to have the document ID. This is outdated. As you can see, it's actually supposed to print out the file name, which is useful for the user, not the ID. Cool. Thank you, everyone, for joining. Hopefully, it was not too technical and not too high level for you. I think it was a good mix. Hopefully, you had a good time. Make sure to subscribe to the newsletter. This is going to be published in our blog, so it will have a longer format with all references, links to articles, frameworks, libraries. I used to do the parsing, the chunking, so that's very, very helpful. And yeah, hopefully you will join the next time, and we will continue talking about knowledge.